All right, everybody, welcome back. In the previous video, we were doing examples of uh, average velocity, constant velocity, and speed. All right, and in these examples, we're going to be doing acceleration. Now, one of the things that characterizes acceleration is that by definition, it's a change in velocity. And so we're seeing in these problems that our velocity is going to change from one value to another value in a certain period of time. All right, and so that's what acceleration really is, a change in velocity. So in this example, we say, suppose a plane starts from rest, all right? And anytime we see these words, starts from rest or ends at rest or stops or anything like that, it immediately means that we have a velocity of 0 meters per second. We won't always see that in a problem written out the way that it is right here. So this says this happens when t0 is 0 seconds. So we're saying at the very beginning, when the plane starts flying, all right? So if this is a starting point, all right, here's his ending point, that we are going to have an initial velocity of 0 meters per second at 0 seconds. All right, so a certain period of time is going to happen. This plane is going to start accelerating down the runway. Now, accelerate means we're going to change our velocity. So after 29 seconds, all right, so at 29 seconds, we now have a new velocity of positive 260 kilometers per hour. All right, so this is our evidence that acceleration has occurred, all right? The fact that we started with no velocity and now we have a velocity of 260 kilometers per hour means we must have accelerated. And we don't know that value. That's what we're trying to determine, the average acceleration of the plane during this time, all right? Now this should work out really well. We have an equation that has acceleration, initial velocity, final velocity, and essentially a time interval, t final minus t initial. And if I look at that equation, this is what it is. It's acceleration is equal to v final minus v initial over t final minus t initial. So anytime we see a delta anything, right? So this is the equation that we have up on the board, but anytime we see a delta, that means final minus initial, and so we can rewrite it in this form, all right? Now, this would all work perfectly. We just plug in all of our values for t initial and t final, v initial and v final, and calculate it, except the units here, kilometers per hour, are not correct. We needed meters per second for that. So everything's got to be in meters and seconds for us to use meters and seconds and get meters and seconds as our answer, all right? So this has got to be a conversion before we do everything else, all right? So before I use that equation, let's go ahead and convert that 260 kilometers per hour, 260 kilometers in 1 hour, and we're going to get this into meters and seconds. Well, there's 1,000 meters in 1 kilometer. That'll cancel out my kilometers. We have 3,600 seconds in 1 hour. That cancels out my hours, leaves me with my meters per second, which is 72.22 meters per second in that positive direction. All right, so that is what I'm going to prefer to use over this 260 kilometers per hour. That's not going to help us, so we're going to change this up here to our 72.22 meters per second, and that's what we're going to use in our acceleration equation. All right, so in our acceleration equation now, we have v final minus v initial over t final minus t initial, and we identified all those by reading through the problem and writing down our givens and our unknowns. So our final velocity here is 72.22 meters per second. Initial velocity, 0 meters per second. Final time, 29 seconds. Initial time, 0 seconds. Plug all this in and do a little bit of calculation. And what we find is we get a positive 2.49 meters per second squared for acceleration. All right, so that is our rate of acceleration. We are changing our velocity by positive 2.49 meters per second every second. All right, so there's our first example. In our next example, we have a drag racer, and he's crossing the finish line. What we notice here, we have velocities again, we have times again. All right. So I see a changing velocity, I immediately know that we're going to accelerate. I also see these words down here, average acceleration. So a drag racer crosses the finish line and the driver deploys a parachute and applies the brakes to slow down. All right, so slowing down is acceleration. I know that I'm going to change my velocity. When T initial is 9 seconds and the car's velocity is 28 meters per second. All right, and so when the time is 12 seconds, the velocity has been reduced to positive 13 meters per second. So we want to find the average acceleration. So what's happening here, all right, we have a drag racer. He crosses the finish line and he starts to slow down, right, using a parachute and his brakes, okay. And we're saying that when he crosses the finish line, he has a velocity of 28 meters per second in that positive direction. And that happens at 9 seconds. All right. Now at the end of this, when he's slowing down, he now has a velocity of 13 meters per second. Okay. And this is at a time of 12 seconds. All right. So we are going to use these values to find our average acceleration again. All right. And just looking at our givens and our unknowns, same equation as last time. Acceleration is final velocity minus initial velocity over t final minus t initial. So we let our variables pick our equation here. All right. Givens and unknowns, they all have to be in that equation. So when we substitute all of our values in here, our final velocity is a positive 13 meters per second. We're going to subtract our initial velocity of positive 28 meters per second. All right, divide that by our final time of 12 seconds minus our initial time of 9 seconds. All right, and we see up here that we get a negative number. 13 minus 28 is going to be a negative 15. All right, negative 15 meters per second. 12 minus 9, that's going to give us 3 seconds. That gives us a negative 5 meters per second squared. All right. And so this means that this car is going to slow down. Now, why is it slowing down? It has a negative acceleration, but its velocity is positive. It's in the positive direction, and acceleration is negative. That means we're going to have a situation where we slow down. All right, in this last example, we have a car or a cat falling out of a burning tree onto a trampoline, and that's held by several firefighters. The cat falls with a constant acceleration of 9.81 meters per second squared in the downward direction for 2 seconds. What velocity does the cat hit the trampoline below? All right, so we're looking for a velocity. All right, now that might make us think that maybe we're going to use a velocity equation, but immediately I also see this word acceleration. And so I know I am not going to be able to use the velocity equation. I have to use the acceleration equation because that's one of my givens or unknowns. It has to be in my equation. All right. So here I have a 9.81 meters per second squared in the downward direction. Okay. So if I'm drawing my picture here, I have my tree. All right. I got my cat. Meow. All right. And what's he doing? He's falling onto a trampoline down below. All right. And so he starts with an initial velocity of 0 meters per second because he's falling from rest. All right. And when he gets down here, he's going to hit this thing with some unknown velocity. So the whole time he's falling, he is accelerating in that downward direction at 9.81 meters per second squared. But since it's downward, we have to make sure that that's negative. All right. And we know that all this happens in a time of 2 seconds. So if I write down all my givens and my unknowns, I immediately see that, hey, look, I have to use my acceleration equation again because I have acceleration in my givens and my unknowns. I also have a final velocity and initial velocity. So this is the only equation that works for us. If I try to use a different one, it's not right. Okay. So when I go and substitute negative 9.81 meters per second squared for my acceleration, final velocity, that's my unknown, initial velocity, that's 0 meters per second, all right, divided by our time of 2 seconds. So how do I solve this thing? I'm going to start by multiplying by 2 seconds on both sides. All right. Over on the right side here, it leaves me with v final minus 0 meters per second. Well, anything minus 0 is just itself. So I get a v final on that side. On the left side, I get a negative 19.62 meters per second. All right, meters per second is a velocity. And so my final answer is that this cat is falling, all right, at 19.62 meters per second, or has a velocity of 19.62 meters per second downward when he hits that trampoline. So this is the moment right before he hits the trampoline. He will not come to a stop until after he starts hitting the trampoline, and that's a different problem entirely because it's a different acceleration. So he's falling at 9.81. As soon as he hits that trampoline, we now have a new acceleration where he's slowing down, and it's a completely separate problem. All right, but this is our final answer, 19.62 meters per second. There you go. So there are 3 acceleration examples. Good luck on your homework.